And hello everybody, welcome to SkyTour LiveStream for this day, which is the 30th of August 2020. I'm your, I guess you call me a field guide to the stars and planets, but in human form maybe. And that's actually, that should actually be the title of my co-host tonight, who you may well know as Daryl Mason. Hello Daryl, how are you?
Hi Mark, hi everybody, I'm good, and you?
I'm fine. You should be like I've called you before the astronomer's astronomer, you know, and I say that because when I went through school, all of my professors, all of the people that were teaching me astronomy, they had no idea what was actually over their heads except for what the telescope would point at. So they're so focused on their research, they never get to understand the actual sky. Now, I was never fully that way. I was always into being able to understand the sky, understand everything that's going on. And what's over our heads is the most important thing in the universe, right? I mean, understanding the whole sky. That was critical to me. Well, I didn't really ever get a chance to explore that fully until after I started taking astronomy down a different path. The path that you were on for how many years, Daryl? Decades, I would say.
40 years.
40 years as an astronomy. I'll call you an astronomy professional because you did teach classes on astronomy. So I don't think that you're any less of an astronomer than anybody else who's an astronomer, to be honest with you. I think you've got a lot of talents. They're just in a separate approach to astronomy, just like mine is a different approach to astronomy. And I think together our approaches kind of blend in the middle. I like that.
Yeah. Well, whatever instruction I gave was purely informal.
Yeah, well, that's okay. I mean, you know, that's not a big deal. I just think that what you did was you enlightened people. You gave them something to explore other than at the time it wasn't the cell phones and Instagram, but it was actually the universe around them. The sky that's dark over their heads in the city hides a plethora of stars, planets, nebulae, clusters, and amazing places that they would never get a chance to see otherwise, unless they were seeing them through your eyes or through your instrumentation or through your tutelage. So I think that it's probably a really good combination, you know. And I went down that path too. Yeah, it was. I want to say hi to you guys. Hello, welcome. I see Brandy is with us again. Hi, Brandy. Hi, Tara. I see that Gaius Savelis is here. Thank you for coming out here. Ronald, of course, is here. Nice to see you here, Ronald. And you know, we had a few other people that joined earlier that said they were going to drop by. And I saw some names out there. Gina Leone, that's one of them that I saw earlier. Thank you for coming, Gina. Good to see you. Daryl, I know you're here, even though you've talked a lot in the chat already. You're doing a great job out there. Saying hello to everybody. Donald Kunzer's here. Hey, Donald. Brandy, hope everything's going all right. Let me know how things are going. Let's see. I'm sure that we'll see more people as we move forward here. And then there's EOT. How are you? What's going on? Hello. So yes, we are doing our stream tonight. And what is it about tonight? Well, again, it takes looking at the main screen here. If you notice on the left side here, this is the telescope control system over here. But the most important thing is this little guy down here. You see, this is a filter wheel location. This filter wheel right there, okay, this filter wheel has it's a 5-position filter wheel in front of the telescope, actually not in front but back behind the main mirror, and there's a camera behind that, and I roll different filters in. I roll 5 different filters in. The first filter is a very narrow band filter. Okay, so if you think of the spectrum, the red, orange, yellow, green, blue, indigo, and violet going all the way across the screen here in my hands as you can see them. Okay, the narrowband filter takes narrow selections within very specific locations in that spectrum. All right, that region of the spectrum is the region where all the nebulae hide, where all the different colors hide, and where the special things we want to see in astronomy hide. And all the rest creates noise. So we're only pulling out the actual data for the nebulae we're looking at tonight. Now, if we were to use filter number 2, that's filter wheel number 1, or filter number 1 in the filter wheel. Filter number 2 is a slightly wider narrowband filter. So it's the same positions, but slightly wider. So the sky is a little bit more polluted with extra moonlight. Like tonight, the moon is 94% full. And you'll be amazed to see what we can get with nearly a full moon, and even after we have a full moon, and during a full moon, we can capture faint nebula now with the filter that I have here. It just takes a little more patience, but we can do it. So that's how that works, and so the filter we're using, filter number 1 and 2 tonight. We're not going to use filter 5. I'll show you filter 5. I'm going to roll it in now. There's filter 5. You can see more stars. Okay. Now it takes extra focusing because the glass in front of the camera causes you to have to focus a little. So what I'm going to do is I'm going to take a 15-second photo at 16,000 right now. This is 15 seconds, okay? And I want you to see, now it won't be in focus, but I want you to see what it looks like with the moonlight polluting the view, okay? Because right now, and it's also not focused because like I said, the filters cause you to have to focus the telescope a little bit differently, right? So we're going to see now how a 15-second photo looks right here, and here it comes. Okay, welcome to the moonlit night. Now, that's a nebula right there, okay? In fact, that's the Trifid Nebula. The Trifid Nebula in Sagittarius. Now, the moon's only a few degrees away from this. How far? I'll show you. Let's go over to our other section here. Let me grab you a new view. Make it easier to see. Okay, so there's a Trifid Nebula. There is the teapot of Sagittarius. And I'm going to turn off the observatory camera right now, just so you can see. And if we move over just a little bit, okay, and just zoom out a little, well, there's the moon. Right? The moon ain't too far away from all this. Right? In fact, it's pretty bright. So when we take a photo just through the telescope using no filter at all, just straight through, then we see this right here. All right, you can barely see the nebula right there. See that? Okay, now let's do something else. Let's go back and let's actually take a photo using our narrowband filter. And this will show you what's happening. So we roll this through again. I'm going to go now, I'm going down here, right up here. And I'm going to take that 5 and I'm going to change it to a 1. You ready? I'm going to do that right now by advancing the filter wheel to the first position again. Okay, that's the narrowband position. All right. And actually, we'll go to the slightly wider narrowband position, number 2. You can see a little bit more stars. But it's not like the open hole where you could see straight through. You saw a lot more stars. Now let's just do another 15-second exposure of this nebula. Okay, 15 seconds now with the slightly wider narrowband filter that cuts little slots in this, all right? And you get an idea of what we're going to see for this same nebula. Hey there, Kathy Pernisic. Hello, Daisy and Zoe Amethyst. Okay, now you can see the definite blue background, but the nebula is a little bit more clear, and in fact, it's actually somewhat red now. It's not like it was here when it was kind of washed out. You can't really tell. You can see a little bit of the red, but you just add a filter that's a slightly more narrow filter, and look, you start to see more detail. Okay, well now, let's do something even better than that. Let's go back, and let's grab our filter wheel and let's go to position number 1. This is a narrowband filter. You'll notice the stars seem to disappear except for the brighter ones. Now let's take this and go all the way to 30 seconds at 16,000. All right, this is the camera control section over here. So 16,000 ISO or sensitivity. and 30 seconds on the exposure. Okay. The telescope has an auto guiding system, so it's actually guiding on the stars automatically. I don't have to do it. And that makes it really, really cool. So, what's 30 seconds going to get us? Let's find out. Okay, so this is the 30 seconds with the wider narrowband filter. Now let's go to the full narrowband and watch what we see right over there. It's going to be a little bit different from what you saw just a moment ago. This is so exciting. Look at that. Look at this. We're actually taking a picture with a dark sky around. This is dark sky now. We have a dark sky. The filter is isolating the most important parts of the nebula detail and the most important gases in the nebula, which are hydrogen alpha, okay, oxygen 3, which is the doubly ionized oxygen, and silicon 2, the ionized silicon line as well. All right.
Silicon? I thought it was sulfur.
Did I say silicon?
You did.
Oh, I'm sorry. Sulfur 3. Doubly ionized sulfur. I apologize for that. Thank you for the correction. I was thinking about a lot of different elements today in the periodic table, trying to figure out what I think I'd want to use for filters to look at different elements, and I was thinking about the different possibilities, and yeah, I was thinking of silicon and sulfur, silicon. So, but you're right. Thank you, Daryl.
Hey, I was just quoting the guy who told me.
That's fine. I wonder who that was.
It was you.
Go figure. Yeah. But I appreciate that. Thank you. But now look at the difference. And this is only 30 seconds. All right. So now if we go back, all right, to our main view here, all right, and let's check this out again. What we'll do now is I can turn something I can turn off here now, I think. Yeah, I can. Okay. We're going to go now from 30 seconds at 16,000. We're going to go right to a 1 minute exposure. 1 minute when the moon's out is a no-go with any other system, typically. Unless you're using a narrowband filter, then you might as well not even bother to try, because it won't be worth it. You won't get a good result. But we're going to see what we get with a 1 minute photo of the Trifid Nebula with the moon only a few degrees away from it. Now, nearly a full moon. I'm going to show you
Mark,
yeah.
I have a question.
Sure.
Your little camera button you push there to cycle the camera up at the top right. Sometimes I just see a camera icon stay when you push it. Now I see an X. Is that just because you're on the bulb setting?
That's exactly right.
Okay.
Yeah, when I take thank you for pointing that out, because I should have explained that. When you're on the long exposure setting, bulb is the long exposure setting. It's a holdover from early days. It puts an X up there. I can stop it at any time by clicking that X. Okay, and I did not just now, but but now you can see. Look at this. This is a 1 minute exposure of the Trifid Nebula using this narrowband filter. I mean, look at this detail. Look at this right here. You can see this beautiful little piece right here. You got these beautiful dark lanes. Oh, look at those. And just, I guess you have to take it from an astronomer. Okay, when you're talking about dark lanes like this right here, you're not going to see dark lanes like this when the moon's out and taking pictures without using some kind of special filtering apparatus. And to see these like this is really quite a treat, and it's actually something of a miracle, actually, because, and prepare your eyes, this is what we saw with 15 seconds. Can you imagine what 1 minute would have been? This would have been bright white, right? But with the narrowband filter, looking specifically at those particular locations in the spectrum for these particular colors and these particular chemical transitions, elemental transitions in the nebula, look what we get. Wow. I mean, that is not bad. That is not bad at all. Now, the other thing is there's a blue nebula up here. This star is actually illuminating through scattering, and we don't see it here too well. But if we increase our exposure and or the sensitivity, we'll see it. However, what we could do is we could actually use processing later to pull it out. I can give you a little bit of processing right now so you can see a little bit, and you can actually see a little bit of the blue here. And under further processing, I'd be able to pull that out of there even more. But look at this beautiful nebula. I mean, that's really pretty. That's really pretty. You can see all these details. Look at the detail in here. Again, the moon is only that far in the sky from me. You know, it's really not that far away. It's probably, if you went like this up in the sky and held out your arm, it's probably just a little bit bigger than this distance. Okay. All right. Away. So maybe 25 degrees or so away. I'd have to do a measurement, but the fact of the matter is, it's really a beautiful way to go. So what I'm getting at is, we can take photos even with the moon out at full and look at nebula now. We're not restricted, and it's really a beautiful way to go. And welcome to D. Smith and Gas Mask. How are you guys? And Tim F. Nice to see you. Thank you for coming out here and joining us on this 94% moonlit night, and we're still looking at deep sky nebula because we can. You know, it's a lot of fun.
Mark, Donald Gunzer asks, those two stars in the middle are closer to Earth than the nebula? Question mark.
I'd have to go into Sinbad to actually see, but it's likely that those two stars are probably the reason the nebula is glowing, at least in part. And I'd have to look up their distance as well. And you know what I can do here. Let me see if I can actually, while we're waiting, we can leave this guy up for now. Oh, not that guy. Leave this guy up for now, and let me do something here to answer that question, because I'd like to do that. Let's see. All right, I'm heading out to a location now to try to answer that question for you. Let's see what we've got here. I'm reading
The
data.
one is bluer than the other one. I wonder if maybe one is in the nebula and one is a foreground.
Not sure.
Just a wild guess.
Not sure. They're actually they could be superimposed on each other, but they are definitely distinct and separate from each other. Not sure whether they're actually in that position. Let me look here. Okay, I'm trying to find those. That's a measure 20 is given as an open cluster. Okay, I'm not seeing it there. Let me see if I can go to the CDS portal. Okay, I'm in the CDS portal now. Not CVS, but CDS portal. And I see. It's such a bright nebula that all the surveys show it's all pretty much washed out. So I can't get to the stars themselves directly here. I'd have to get them from a different setup here, a different location. For those of you that are wondering where I am, I'm in a database called Sinbad, S-I-M as in Mike, and then bad, like bad boy, Sinbad, like Sinbad but with an M as in Mike. So and Sinbad is a stellar object hunting and or stellar star object data system used by professional astronomers. And what we'll do is we use this to actually find out actual data on, for instance, stars within a cluster. You can click on any one star and get all the information about that star that's available, that's known. That's really kind of cool, you know. So I think that's a good idea. Hey there, Cindy Murphy. So that's what I'm trying to do here. But kind of not finding what I want right here. So I guess what we'll do is I tried Aladdin and I tried Sinbad and the CDS portal, and I didn't find what I was looking for. However, maybe I can find it another way. All right, tell you what I'm going to do. Because you're asking the question, I want to give you the answer. Okay, so what I want to do is come back to our main view here and bring up our planetarium view. And then inside here, the stars we're talking about are these two right here. Okay, and that's the, I believe that we're looking at these guys. That's Hipparchus 88330, and it doesn't tell us as suspected. It doesn't tell me the. It doesn't tell us the distance of the star. I didn't think we were going to get it from that. But how about this other one? 88333. And that's definitely the star that's lighting up this nebula. This is an 07. Okay, so the upper star of the two, the bluer one that I believe you were looking at, Daryl, that's an 07. Most of its light is being given off in the ultraviolet. All right. And again, we're not getting a distance from it. I don't trust little planetariums like this to give us all that right data. That movement you see is because the Earth is moving and we're tracking the stars. All right. So this view here is actually the altitude and azimuth coordinates that we're looking at here. Okay, that's why when those come on like that. All right. So that's the altitude and the azimuth coordinates, and the right ascension and declination coordinates are the celestial coordinates extended out into space, and that's this view, which is different from this other view. Okay, that's that view, and then okay, the altitude and azimuth is like a bowl over your head, where the very top is called the zenith, and then down here is the horizon, right? Well, if we look at the world coordinates extended out into space, it looks more like this. So now you see it's a sphere somewhat on its side, which is true because the North Pole is up that way. So the zenith is not any particularly different place. It's just the spot directly overhead. But it's not like it is with this other coordinate system where it's directly over your head like that. That's just a bowl, BOWL, that you're underneath looking up. And it gives you a altitude, and the azimuth is the angle off of north all the way around you to 360, which brings you back to north. Okay, and if we were to get rid of the zenith and look at the right ascension and declination, you'll see there's no particular reference to the zenith here that gives us anything to look at in particular. It's just these are the coordinates. This is the way the telescope is looking at the sky. And when we zoom in on an object from here, right, like we've been looking down here at this nebula, okay, when we look here at the nebula, you'll notice that when we're looking in equatorial coordinates, that is to say, the coordinates of the Earth extended out into space, nothing's moving. But if we get rid of those and bring in the bowl, well, the stars are moving against the fixed bowl, okay? And so when we zoom in, okay, you'll see that they're moving slowly, okay? But the Earth's lines are always there because the stars are at a certain position and they're measured by the extension of the Earth coordinates out into space, okay? And instead of latitude and longitude, we call them right ascension and declination. And the declination corresponds to the latitude lines, and the longitude lines correspond to the right ascension. And we measure that in hours because it takes 24 hours for the Earth to go around once, so we have 0 hours all the way to 23 hours, 59 minutes, basically, and so forth. So that's these lines, and that's how we actually have permanent locations for the stars. This type of thing, where we're looking at the altitude and azimuth, is for our local observation dome that's over our head, right? So we notice that already the summer sky is well into the southwest already. And, you know, this is, as we said before, this is my view. That's the house. And when we looked at Comet Neowise, we were looking over here. All right. And now when we come back to here, we have a big old moon, big bad moon, okay? And we have Aquarius over here, and Aquarius is the water bearer. You see him there. And also in this constellation is something we couldn't really look at tonight. Well, actually, we probably could, huh? It's actually quite a clear night. It's really, really still and crisp out there. And we're looking, you know, down in Aquarius, we actually have the Helix Nebula, which is probably one of the, if not the, I think it's the biggest planetary nebula in the sky. And I think it's bigger than the moon, isn't it, Daryl?
I believe it is, yes.
It
is the closest it is the closest one to Earth, and it is quite large in the sky.
Yeah. It's also quite low, okay, in the sky. And if you notice, it's actually near the moon tonight. That would be a kind of a cool target to see if we could actually see it. Yeah. Being that close to the moon, that'd be a good test.
You may only be able to grab part of it at a time.
Oh, I know I will. You're right. Yeah, it's a big, big thing, and I have such a small field of view. What do you think of my glass of water?
Hey.
It's a gigantic glass. I drink water all day and just eat a meal a day. That's how I dropped 21 pounds in 3 months. Didn't even try. It just does it automatically.
Bravo.
Yeah. Well, you know, it's uncomfortable with that much weight, extra weight on you. Okay, so if you want, we can also look at Jupiter and Saturn, and then check out the moon, and then maybe look at the Helix Nebula if you like. But before the Trifid goes down fully, I want to take us over to the other nebula that I know we like to look at here in this region, and that's going to be the Lagoon Nebula, if that's okay with all of y'all. So there we go. I told it to go, and you'll see the stars race away, and you'll see a bright star come in as it aligns, and it's going to choose. Which star are we choosing here? Yeah, Al-Nassel. It's using Al-Nassel down here, which is actually it's the very tip of the spout in the teapot of Sagittarius. Here's the teapot. You can see it right there. There's the handle. There's the open body of the teapot. There's the cover, and there's the spout. And right there is the star that we're aligning on. And then once it centers that star, it's going to jump up and know exactly how far to go to get to that what's called the hourglass cluster. Actually, the cluster that forms the Lagoon Nebula. And if we come back to this, we'll see the Lagoon Nebula coming in. And there it is. It's right in here. It's faint. How can we tell? Well, we can actually just take our view here. Sorry about that. We could take our view and just go to the straight through view for a moment, and there you can see the cluster. Again, it's not focused, all right, because it's one of these things where it has no filter, and when you put the filter in, you got to refocus. But you can see the stars are a little out of focus when we do our focus view there. All right, so going back to our view here of the nebula, we give it about 11 seconds to gather a guide star, which it doesn't have any problem there. Okay, and then we take we'll go for a 1 minute shot right here of the Lagoon Nebula. All right, and while that's happening, I can come over and say hello to Bonnie on Ahata 77. How are you? And Cielophiles. That's what we are. We're Cielophiles, yeah. Skyophiles, you know. There's actually a famous planetarium called Cartes de Ciel, which is the sky. It's a planetarium for the sky. Chart of the sky. You ever use that, Daryl? That program, by any chance?
No, I never have. Sounds French.
Yes, Cartes du Ciel. No.
Not that there's anything wrong with it.
Well, but I've never. I tried it, but it doesn't have the same kind of beauty as this right here. This one, this guy here is really by far the most beautiful planetarium program there is. So I just really like it very much. And look at that. Now that's not bad. At 1 minute for a moon being out. Look at that. Wow. You can see all these dark nebulae in here. This is what I like about this nebula. This is the cluster that makes up the Lagoon Nebula right here. A lot of these stars contribute to the glow a little bit, but the most important star in this entire cluster is this guy right here. You can't really see him too well. Let me zoom in and see if we can do that a little bit. Okay, easy. It's hot. Okay, so now you see that little star right there. That star is a very hot young star, and it's responsible for illuminating a lot of this cluster. I should say illuminating, causing it to glow through an atomic reaction with the hydrogen atoms. It's forcing these atoms to glow, as we've talked about before. And so it's really beautiful, and you can see a lot of interesting detail in this nebula, especially when we look right here. Look at this. This is such a beautiful little black line of dust that's obscuring the nebula behind it. Okay, the nebula is behind it, and it's up here in the front. Okay, in front of it, and that actually makes it something that's, you have to understand the 3D nature of the universe. Okay, and that's what we're seeing here, the 3D nature of the universe on display. So it's a really cool nebula, and the fact that we can actually photograph it with a nearly full moon out is testament to our equipment and how it's working. We could do beautiful photos no matter what, and we're going to. So never mind the moon, we're just going to be doing narrowband shots when the moon's out, right? And so we can look at anything no matter how faint, and we're going to try and do the Helix as well. Now the Helix Nebula is very faint anyway, just so you know. It's very faint anyway, so it's going to be hard to capture it. All right, now what I have to do is in order to get over to Jupiter, I have to make sure that we can actually see it. But before we do that, let's just I want to take us up, not to here. I think isn't it up here? Yeah, here it is. I want to take us to this cluster. It's one of my favorites. All right. It's called the Wild Duck Cluster, Messier 11. When Charles Messier saw this, he thought maybe it was an object that could be mistaken for a comet, and they marked it as an object to avoid in your hunt for comets. Yet it's one of the most beautiful clusters of stars. It's not a globular cluster. We're familiar with globular clusters like Messier 13, right? And Daryl's favorite, Messier 22, which is down in Sagittarius. But I don't think that Messier 11, it is not a globular cluster. It just happens to be a fairly dense open cluster of stars. An open cluster is different from a globular cluster in that age, for one thing, but globular clusters tend to be filled with anywhere from 20,000 to 60,000 or more members within the cluster. But open clusters tend to have a few hundred at the most, and that's the distinction. And so when we look at this one, that's what we see. We actually see a cluster that has far less members than a globular cluster would have. So let me just take us back to the straight through view, And measure 11 is right there. You can just barely see it. Do you see it right there? Yeah, it's there. It's really faint. Not. It's right there. Right by the arrow. Right there. All right. And let's go back to our narrowband filter, because that brings us the best views. And we're going to do 30 seconds on this. I had to give our telescope time to make an alignment. I'm sorry, get a guide star. All right, and off we go into the wild duck yonder. And so as we head, yeah, quack, yeah, right, quack, quack. That's right. So we'll do that, and as we get over there, I tell you though, Daryl, you know, the narrowband filters just changed life, didn't it?
Sure is.
Changes life. You have one. You have the Oxygen 3 filter.
Yeah, it's a pure O3 filter. It's a very narrow band. It looks like a mirror when you look at it by eye.
Yeah, same with this one.
Yeah.
Same with this one. Okay, this is Measure 11, the Wild Duck Cluster. Look at all the stars in there. Oh, we got a little bit of walk, so I'm going to get a good one. Sorry. I want to make sure we get a good one. But this little cluster is really quite something, because it's got so many members. Many of these stars out here might very well have been ejected members of this cluster. So we have to look at these stars. See, when you look at a cluster of stars, what you see in the sky may not necessarily be all there is to it. There might be more to a cluster than just what you see visually. There might be some enveloping gas that's still there, that's not being caused to glow. So there might be vestigial remnants of what the cluster formed in. Let's see if this was better. Yeah, this was a little better. So look at that. So these are just amazing. It looks like a globular cluster, but it's not. If you think it's a globular, but it's not. It's chiffon. Do you remember that commercial? Oh, man, that really dates me.
I remember Montequilla.
Oh.
Parquet.
That's right. Is this parquet? Yeah. How beautiful. Yeah, so that's measure 11. And if we look now, we're kind of in the northern Milky Way. We're above the Sagittarius star cloud, which is down here. Okay, that's toward the center of our galaxy, where the supermassive black hole is. That's a driving force in our galaxy. And then this is interesting. This is it's labeled a possible binary cluster, and I want to check it out, even though I'm not sure that we're going to see much of anything here. But, you know, it's worth looking at, isn't it? Okay, this is NGC 6755. And we'll see which star it's going to pick. Okay, it's going to bring us over to Almazani. And then it's going to go over to that. It's going to go to the box, because it's this box that I told it to go to. So we should have both in the same view. Wherever this is, I probably should have shown you. Wherever this star is, the star that was just there, that's where the center of the box will be. Okay. There we go. So, Daryl, have you had any telescope time in the last couple of weeks here?
Only here.
This is it, huh? You haven't gone out?
Weather hadn't been cooperating.
Oh, that stinks. All right, we'll do a 30-second shot at 30 seconds at 16,000 sensitivity or ISO and see what we get. Meanwhile, I'm also going to start up our cam, which is probably going to be a bit overwhelmed by the light, so I'm only going to go to 30 seconds or so for that. And I'm going to auto apply some processing so that I can do that after. We're going to take one picture after another. We're going to auto save that image, and we're going to say go. All right. So now we can come out of there. So this is just a 30-second shot, and we should see it come in right now. Let's see what... Oh, how about that? You can actually kind of see... You see one here. You see one of the clusters there, and look at there's the other one right there. That's very faint. Or is it here and here? I can't tell. I've never seen this object before. But yeah, look. 1 and 2. What's interesting is when we actually... we talked about this before, actually, on SkyTour Radio, and that is that where was our sun actually born? We look at other clusters, we say, well, you know, we have stars that are born in many of these clusters, and then they drift away from these clusters and find an orbit around the galaxy by themselves. As Daryl and I have talked about before, you know, we've gone around our sun, around our galaxy core, around the nucleus of the galaxy, 19.5 times since 4.6 billion years ago when we were formed. And in that time, a lot of mixing takes place. So trying to find our original location, the place where it all began, that's a mystery. And we're trying to find it. So what we do is we try to find stars like our sun. And for the longest time, we've searched for a star that's not just like our sun. Our sun's a G-type star. Okay, that's one of the OBAF GKM classification. It's a G. It's a G2, in fact, number 2. Out of it goes G0 through 9, just like B0 through 9, O0 through 9, etc. The G2 is us. Well, we found another G2 star, sure. However, if it's born in the same location, then the chemical abundances in the star that are made with the star when it first forms should be nearly identical. And a lot of the G2 stars we've seen just don't have it. Alpha Centauri's, one of the stars is a G-type star, and it doesn't have that composition at all. Nearest star to us. Well, again, in 4.6 billion years, a lot of mixing is going on. A lot of passages of other stars have happened that have nothing to do with us. Well, it turns out that astronomers, for the first time, have actually found the sun's twin, meaning that this particular star was most definitely, and the certainty is about 95%, that this star was formed when we formed in the same location, in the same group. So we found one of our siblings. That's like finding out that's like finding out you had a brother you never knew you had, or a sister you never knew you had. Okay? Well, we found out we have a sibling we never knew we had. And it's a stellar sibling. But man, let me tell you, this is really important news. Hey, Rockstar, how you doing? So I think that if we look at these faint clusters, like this little cluster down here, I mean, it might be faint, okay? But, you know, there's a lot of stars in here that might be just like the sun. And these clusters tend to be far away. We thought that we came from one particular cluster, and Daryl knows the one. We talked about this before, and you said it on the show, Daryl. Do you remember? The knowledge we used to think we knew where we came from.
Oh, the Ursa Major moving group.
Right. There was a thought process at one time that the stars that make up what is now the Big Dipper to us, what we see as the Big Dipper, well, we see them as bright because they're actually relatively close, some of them. And we thought, hey, by looking at these stars and their motions, is it possible that we're all moving together and that maybe we all came from the Ursa Major location, that group of stars that are all moving together? It's not just the stars in the Big Dipper. There's many others that are in that moving group that you can't see. They're much fainter. Well, the answer is that it turns out that after an analysis and computer simulation, it turns out that no, we're not part of that. Oh, well, sorry, you were my daddy, but now you're not my daddy. So that wasn't the culprit. That wasn't our birthplace. So then they thought, well, maybe it's Messier 67, which is a cluster that has stars sort of like the sun. But the problem is it's a couple thousand light years away. Actually, more than that. And for the sun with its planets, because the planets would form at the same time. All right, we see planets forming at the same time with the main stars, actually, where we look at these protostars forming out there in the universe, the Orion Nebula in particular. And the planets are formed at the same time, but when you have gravitational interactions where stars are all moving around each other, all these many stars in a cluster, and one of them gets whipped out, for a star to get whipped out at the velocity needed to put us here now where we are, versus where that cluster is now, the forces involved would have stripped the planetary gases that were forming planets around that early star away, and we would not be here. It would have just flung that star out all by itself, and any gas that was making planets would have been left behind. And not only that, let's suppose that somehow they did survive. Well, you can imagine that at the speed the star is moving, these planetary protoplanets trying to move in a circular orbits like we see, would be dragged out into long ellipses. Hey, wait for me, as the star's racing away. They'd be dragged out into these long elliptical orbits, and we'd have all these elliptical orbits here in our solar system, and we do not. So that's not right. Something's wrong there. So the thought process is that Messier 67 may not be the one either. And then we find this one star that has the exact, and I mean really, really close to the same chemical abundances as our sun. And that means that maybe we've found a sibling. We think that 95% chance that that's one of our siblings. And that means now that we have half a chance of finding our original birthplace by reverse engineering our position in correlation with that star's position. Where is that star? Way down south, minus 79 degrees, or otherwise I would have shown it to you. You know, so that's how it works. Hey, Side, how are you? I'm a label heretic for. He's saying the sun is hollow and not burning anything. I know I may be labeled a heretic and imprisoned for thinking this. I've given it careful thought. Well, you know what? I'll give you an example. When I was getting my astronomy degree, one of the things I had to do was actually build a star on the computer. We actually had to build a computer version of a star that would actually function and do all the things that stars do. Oh, okay. Good night, Brandy. Thanks for coming.
Night, Brandy.
Thank you. I'll look for that email. Thank you very much. Yeah. So, in building the star, we could see that the star actually was doing what stars are supposed to do. So, I recognize and understand that there are people that feel that some strange things are going on out there, and I can't deny that there are many things that are going on out in the universe that we'll just never understand, at least not for a long time. But we do have a pretty good idea on how the stars work. We really do. And so we may not understand their cycles. We may not understand their when they're going to explode, when they go supernova. But we do have a pretty good feel for how they actually work. You know. So, and I don't think that the way they work is that they're hollow and not burning anything. Well, they don't burn anything anyway. They actually fuse things. Fusion is strange. It's a process by which atomic nuclei under high pressure, and they're just nuclei, not atoms, just the nuclei of the atoms are pushed together, and they can actually form other elements in the periodic table further down. So hydrogen, hey, there's Jupiter right there. Okay, hydrogen, for instance, is pressed together to make helium. Now, how that really happens is that the hydrogen gas first gets a neutron from other reactions. The neutrons are given off in some of these atomic reactions. And this happened last time, Daryl. I'm going to Jupiter, and all of a sudden it just whips away. Again, database issue. Don't know why. We'll get it back. All right. So, if you get a neutron in your atomic nucleus, that makes the hydrogen atom with an extra neutron in it what's called a variation of hydrogen, or a different type of hydrogen atom, and that's an isotope. Okay? And we call those isotopes, yes. And so when we look at these isotopes, adding a neutron to a hydrogen atom makes it deuterium. All right, and a deuterium atom has a proton and a neutron. Okay, now that that goes and collides with and is pressed together with another hydrogen atom. And now you have two protons and a neutron, okay? And that makes a helium isotope. Two protons make helium. And then the process goes on, that process goes on to actually form another isotope of helium called helium 4. And then that liberates another hydrogen to start the process again, all right? So when we're talking about hydrogens made into helium, it's actually being made into isotopes of all these things. It's not hydrogen and helium, it's isotopes. All right, so that's what we talk about when we say that. Okay, so let's see here. I'm going to do this. Okay, I'm going to bring us back up here. I don't know why it does what it does, but sometimes it does this. It's database error. There's Jupiter. See, the telescope knows where it's going, but sometimes there's a database error. Okay, Daryl, we got some Galilean satellites tonight. What do we got?
You could probably find out faster than I could.
That's probably true. I just could zoom in, huh? I just want to okay, so all right, on the left side here we have Europa. All right, and Io is actually behind Jupiter right now. That's interesting. Okay, it looks like Io is firmly behind Jupiter. I'm not sure how long it takes for it to come back out. What do you think, Daryl? You know the timing on this?
Actually, I saw that somewhere a day or two ago. Give me a minute, I'll look it up.
Okay. Because we can watch for the reemergence of Io.
Look stuff up.
Well, it might be in front of Jupiter, actually.
I will have an answer in just a second. I think it may well be in front of Jupiter.
Okay. Well, then what we're going to do, we're going to see if we can see a few things. Let's try this. Okay, we're going to come down from 16,000. You'll see the image get dimmer. Let me actually do this, guys. Let's center it up for you so you can see it. And let's go down to 50 ASA, which is the lowest that my camera can go. Okay, and then we're going to drop the exposure. See that? And again, we're using the narrowband filter. So let's just do this half-second exposure with the narrowband, and let's go. What's going on here? Where'd it go? Okay, commands were being bunched up.
Io is in front of the planet, and its shadow, if we can't see it already, should very shortly be following it across the planet. It will be on the left-hand limb.
Yeah.
Eastern limb of the planet.
Because I was
right
going
now.
this way, I believe.
Yeah.
Okay, and the shadow should be right there. We might be able to see it. Let's try. Let's try something here. Now with planets, you know, we don't necessarily need the filter. So let's go to the straight through. All right, and we'll have to refocus, but that's fine. Let me get us over to where we can refocus. Okay, so here we go. Wrong way, Feldman. And then we come this way. Alright, and now what I'll do is I'll get us in this focus mode here. Alright, that's the focus mode, and now I can focus. Alright, I go the other way.
Ganymede and Callisto on the right, by the way.
Thank you very much. Am I focusing on Ganymede? I must be, because it's the brighter one. I assume this is Ganymede.
Yes.
Yeah. It's brighter, so it's the biggest moon in our solar system. In fact, if it was a separate object, it would be called a planet. If it was orbiting the sun separately. But it'd be marginal. Alright, let's find out if that did anything. Okay, now we're going to shorten the exposure up a little bit. Like that. And let's just do a quick shot. Yeah, why is it? Oh, I know why. Darn it all, I keep forgetting. I got a 5-second delay in the photos. No wonder it's taking so long. I'll go fix that right now. As soon as I get my picture back. Okay. Okay. Alright, there we go. Okay, so now, here comes Jupiter. Okay, it's not quite focused. We gotta focus this a little better. Alright. Let's do the focus thing. Okay. And let's do this. And bring it in. Bring it in for a hug. Here we go. Yeah, alright. Thanks for bearing with me, folks. I'm just trying to get the focus straightened out. Okay. That might be it. That might be it. Let's go see.
Why were you having a 5-second delay in your images?
I had a 5-second... oh, there's the shadow right there. You can see the shadow.
Uh-huh.
I had a delay in there because I was doing a test out there, and I was doing a 5-second delay before taking the picture. Yeah. My mistake. Yeah, you can see the shadow, guys. It was right there. You see that little darkened area? Actually, this shows it pretty well. See? I was blending in with this band, but the shadow's got that little ellipsoid look to it. And we come back here. You can see it right there. See that dark area?
Barely.
Yeah. It's there. Io is right about here. Hard to tell. I could actually try to see if it's a focus issue one more time and try and do some critical focusing again. Actually, what I'll do is I'm going to do this. I'm going to take this up here, and I'm going to make this even bigger. So there's my focus area now. Alright, and now I will focus again. Okay, so we're out of focus, and we're coming back into focus. And then we just went out of focus again. Actually, it might be better to focus on these guys over here. So we'll focus on those. Should have done that before, sorry. Okay, that's out. Yeah, it's tough focus tonight. That might be it. Let's try it. Welcome to Real Astronomy, folks. I don't mind. By the way, you might want to keep looking for Amanda in the chat. If she's available, she's going to join us. Okay, let's go see. Oh, that's better. Now, look at that. Look at that, Daryl. There's the shadow. Is it not clear?
Give me just a moment.
Okay.
Yeah.
Yeah.
We can see the shadow.
Look at that. There's a shadow of Io right there.
Io itself is still lost in that thickening in the clouds in the upper band.
But look at that, huh? It's actually a really good view. That's a nice view. So the critical focusing helped out tremendously. We got it right to that point. But there's a shadow of Io on the planet, guys, right there. Can you imagine? We get so excited about an eclipse, and Jupiter is 89,000 miles across, so that's pretty big. If you were at the top of Jupiter's atmosphere, the planet would look flat to you every which way you looked. It's so big. You know?
Mark KDQ asked a question: what is the surface of Jupiter? I said, or tried to say, what we see there, we might think of as the surface as just clouds.
Yeah.
The actual surface, I forget. I know they say it's not rocky now. Is it metallic hydrogen, or is that farther down in?
Yeah, no, the metallic hydrogen is the core, basically. There actually might be a rocky core, but it'd be very small relative to the rest of the planet. The planet is made of mostly hydrogen gas with some helium, but the cloud bands are due to a tiny, and I mean tiny, fractional impurity in that planet's composition. And then before, by the way, just so you, in case you just didn't see it, that right there, that's the Io shadow on Jupiter right there. That little tiny black blob right there, and it looks elongated because Jupiter's a sphere. And so the shadow is being, shown. It's going around the edge of the planet, a little around the forward edge like that, and it's wrapping a little bit. Io was right about here, right about there. Maybe a little over there. I'm trying to figure out the best way to show you this. Kind of hard, but it's actually right about there. All right, it's right about. Oh, I can see it. There's Io. Look at that. That's my finger. Okay, I didn't show my finger. Look, there's Io.
Well, you had the eye right anyway.
See, I think that's Io right there, and you can see the shadow. We'll take another photo, and we're just looking through the image right now. I'm gonna go to a 45th of a second, make it a little bit longer, shorter exposure. See if we can see that better. No, it doesn't look better to me. Alright, let's just go back and make this go a little longer. Let's go back to a 30th. We might have had a moment of good seeing there. Oh no, we still have the shadow. There's Io's shadow right here. Right there. The little black dot. That's the shadow of Io, and you can I think Io is right here. You can see a little dark nodule right there. That's pretty cool. This is a good one. This is a really good a good phenomena that you can watch, because if you notice, this was the shadow of Io here was closer to this side earlier, and now it's actually moving out onto the planet, because Io is going this way around the planet. It's going this way around the planet, so that is to say counterclockwise when seen from above. All right. Hey there, Brian Levitt. How are you? No. See, Brian, he says that he thought there might be too much moonlight for a show. No, we're using a narrowband filter for the nebulae, and just so you see, since you just got here, I'll show you. When we were taking pictures of a nebula before, we got this. Whoops, not that. We got this. This is a 1-minute shot of the Lagoon Nebula that we took earlier. And then we took pictures of the Trifid Nebula, which was this guy here. Okay, I mean that's really pretty for 1 minute under moonlight, and that's because we're using a special narrowband filter. So very, very nice. We're very, very excited about that. And then Jupiter tonight, we're taking these pictures. Now this is without a filter. We're not using a filter tonight, and for Jupiter, because we're actually looking at the shadow of Io, the closest moon to Jupiter, passing on over Jupiter, and here you can actually see the shadow of Io right there. There it is, that little black dot right there. And Io is traveling semicircularly, elliptically, almost around orbit around Jupiter, and it's going, this way. It's going to go around, and it's actually, I'm sorry, this way. It's going, counterclockwise. So from the top, it's traveling from left to right across the face of the planet, and then it's going to go around behind the planet, and then come back out around the front again, like that. And if we take another photo, you'll see the shadow will be even more to the right side, just a little bit. So we'll just go take another photo right now and see that the shadow has moved a little bit more, and I suspect it will have. Yeah, it's a little bit, this photo is a little, it's there, but it's a little bit washed out. Nice thing about this is because they're just 30th of a second shots, we can just keep taking pictures until they come out better. All right, and there we go. So now we can actually see the shadows here right now. Okay, and Io is right around here. Earlier I had it, I caught it with my eye, saw Io was right over there. The eye, as Daryl says, I got the eye right. But it's kind of fun, to look at these things. I mean, it shows you that the universe is in motion all around you. Look, I mean, we actually watch the shadow moving. It's just a cool thing to see and watch this shadow actually moving. And don't forget, Jupiter is very far away, but it actually has a lot of satellites, a lot of moons around it, including it has a faint gossamer ring. In fact, it seems like gas giants having rings is more of the norm than the oddity. Gas Mask says Elon Musk wants to make travel to Mars possible as soon as possible, and he's correct. Elon Musk does want to send people to Mars. Notice I don't say a man to Mars, because most likely the first crew is going to consist of a female and a male, and maybe 2 of each. Not sure. Okay, Donald, thank you for coming out. Thanks for joining us. Good night.
See you, Donald.
So I think that's pretty cool. Let's see if we can. We see that shoulder. We see that shadow right there. Let's see if we can capture it again. Doesn't take long to move. I mean, it moves across. I don't really see it. No.
Should take about 5 hours, just under 5 hours to transit from limb to limb.
Well, the seeing doesn't allow us to capture it perfect every time. What if I go 1/20th of a second? Make it a little brighter. Yeah. Oh, I see what's going on. We actually have the focus has gone soft on us. That's probably due to temperature change out there. Well, it's okay. That's okay. Let me get us. Let's get us to find. I want to get the focus again. Hold on. That's what I want. Okay. Now I'm going to reduce the exposure a little. Get this dimmer. No, I'm sorry. I'm going to go brighter because I want to bring up one of the moons. And it's these moons that we focus on. All right. So there we go. Move the telescope over. And now I'll focus on the moon. I might have just done it. Alright, so it's out of focus. Put it in focus. That might be it. Let's find out. And let's just take a photo like this. We can see the moons. Alright, maybe. Maybe. Okay, let's do this now. Let's do this right. Let's do... Oh, let's see. Shorter.
Question, suggestion, possibly?
Sure.
What if you took a short snatch of video and then went through frame by frame, looking for moments of stillness, good seeing?
Yeah.
I know that might be a lot of frames to go through.
Yeah, no, that's the benefit to that. What you're saying, of course, is amazing. What you do is, this is better focus. What you do is, and this is for people, Daryl knows what I'm talking about. You take a short video, say 20 seconds, 30 seconds, and if you're shooting at 30 frames per second, well, then you have 600 frames after 20 seconds. That's 600 separate photos that you can stack and get a final good image out of. And we could, for instance, take 30 seconds of video here and try to stack it and see if we can pick out Io over the planet and its shadow. Or we could just take 30 seconds of video and then go through each, through 600 frames and see if any one of them shows better than the others, because there will. The scene comes in and out and changes like this, right? You can see some modeling in these bands, but earlier we could see the shadow quite nicely crossing. Right now, the shadow seems lost in this band over here.
Yeah.
And that's okay.
I was thinking more, some night of serious imaging.
Yeah.
Maybe not so much while you're doing a live stream.
No, because that would take...
Yeah, well, you'd have to wade through all 600 images and pick out the ones you want to stack. And
yeah.
that'll take time.
Yep. Hey there, Katie Q. Hi, DK. How are you? Good to see you guys. Okay, so that was cool. We actually got to see the shadow of Io on the planet. I thought that was neat. Very cool. And while we're here, why don't we head over and check out Saturn? And we're getting closer and closer to the moon. See, if we back out a little bit, you see the moon's there. Yeah, not bad. But with the narrowband, we're doing pretty good. All right.
You've been doing a lot of west-east motion tonight instead of your normal north and south to stay within the confines of your shutter opening.
Oh, I know.
Wonder if you're going to have to go move the dome sometime or other.
I moved it so that this might be the one that forces it to happen. Because we got lucky. Okay, we're up at W right now, and it's gonna then come down to Saturn here in just a moment. But we gotta show it to you. There it is. That's the star we've been on here. Now we are, of course, in white light. All right, and we'll have to change over to filter number 1. Oh, no, we won't. We're going to do this with Saturn again. Here's Saturn. Well, let's see if we have that same database error that we had last time. Is Saturn going to stay, or is it going to go? Let's find out.
I think I see several moons.
Yeah. All right. See, Jupiter, for some reason, it's wrong in the database, and it has a different position. The calculation's wrong. Okay, and we do see several moons. And let's just do a quick zoom here just to see. Oh yeah, look at that, Daryl. We've got 1, 2, 3. That's probably Titan, I would think. Out there. Let's find out what those moons are, shall we? Let's come out of this and go into our planetarium view and center it up and check it out. Yeah, that's Titan out there. And what have we got interior here? We have Tethys, we have Rhe, Enceladus, and Tethys. Alright. And Mimas is down there. I don't know if we'll see Mimas. Let's go check it out. Let's just take a photo. Not 30 seconds. Let's do... I don't think 10 seconds at 50 is going to work, but let's just try it. We are straight through. It's going to be kind of bright. All right. Well, there we go. Okay, so here's Enceladus, here is Rhe, and here is Tethys. Okay, and what was that one? That, of course, up there is Titan, second largest moon in the solar system. What's that guy? I know that Mimas is down here, but Mimas is kind of small, so I must have missed it. So let's go check out which one that is really fast.
Enceladus isn't very big either.
No. Oh, that's Dione. Is that Dione? Oh, yes, Dione out there. Yeah, Enceladus is tiny. And it shows here, see? And I know we haven't seen the rings yet. We're going to get to that. But I just want to take us back. This is the live view now, and what we're going to do is focus on this. We should actually just try that, shouldn't we? Let's just try a shot and see how good it looks. Okay. We'll go 1/8 of a second. Yeah, we'll get rid of the focusing. There we are. Wow. That looks pretty. Look at Cassini's division. Holy cow, isn't that Cassini's division right there?
It is.
We can actually see
you can faintly see the crepe ring across the face of the planet right there.
Yeah, there it is.
Just above where the ring is crossing the front of it.
Yeah, right there. That's pretty nice.
And you can see the planet's shadow up at about 10 or 11 o'clock
right
on the ring right there.
Yeah. Yeah, we can. And if you want to know what we're actually talking about, you see this division in the rings here, guys? That ring, right, division? Okay, if we come back to here, okay, here's what we're talking about. This is that division we're talking about there. That's called Cassini's division, a famous apparent gap. It's actually definitely filled with material, but it's less dense. And this is the crepe ring he's talking about. See how that looks? It has that little kind of faintish sort of ashen look. We can actually see that here, right? And we can see Cassini's division as well. Not bad. And that's without going after the focus some more. I'm going to actually try to bring up some moons so I can actually focus. We'll focus using Titan. Actually, could use more on all of them. We'll do it this way. Very cool.
Titan has an appreciable disk.
Yes, it does.
If that might be harming your, trying to make it as small as possible.
Well,
to achieve a crisp focus.
Yeah, it just I'm just wondering if at this distance it's going to make a huge difference to us. It might not, but it might. There's something else I'm trying to do too. I don't know if this is something you've done before. You get it to a certain point where the image begins to actually dance around more. And with point lights, point sources, that's actually more noticeable. So right now I'm getting Titan to dance a lot. Let's see if it actually has made a difference. Because your suggestion's a very good one as well. Let's see if I can drop us back down to an 1/8 of a second here. I'll do a 1/6 of a second here. Let's see what that looks like. I don't see that much of a difference. Alright. So why don't we try what you said? Let's try that. And maybe it'll work. Okay, let's go bring that up. Maybe what I can do is go this way and go this way and pull that star in. Okay. And now we'll do that. Okay, definitely out of focus. I'm hitting the focus buttons right now, guys, out in the telescope. It all comes down to a personal preference about where you think focus is. And then the telescope proves it one way or the other, whether you're right. Okay, that looks like that might be it. Now, if you think about it, what's focus? It takes an object that's sort of distended and makes it the smallest it can possibly be. So I'm writing an autofocus program that will actually focus for me. And it'll operate the buttons. It'll kind of basically do it electronically. And we can make it look at the image and make the image as small as possible. That's all it has to do. It doesn't have to think anything beyond that. It just has to make the image as small as possible. So it has to measure it and make it as small as possible. If it can do it, we're golden. You know, and that's what the focusing program is going to do. I've never really written a focus program, so it'll be kind of interesting to see what happens. All right. Let's do this. Let's drop the... Let's go down to... Let's do 1/6 of a second now again. Let's see what we got. Oh, no, I see Cassini's division again. You can see Cassini there, the crepe ring. And
that might be slightly better.
Yeah, it definitely is. Okay, so what we're looking at, guys, is this.
One thing you can note when you see the planet's shadow on the ring behind it to its upper left there at about 10 or 11 o'clock, you only see that because the planet is either before or after opposition. After opposition in this case, when the planet is at opposition, its shadow is directly behind the planet and we can't see it.
Right, right.
So now we're seeing it at a slight angle.
That's the shadow right there. You can see the little edge of the shadow from the big, from the circular part of the planet's body, and aimed down to the back of the rings. One thing we can't see is the shadow of the rings on the planet. Unfortunately, can't really see those. But that's really pretty because you can see all this delicate detail. And when Cassini Saturn sent back images, it sent back images of these beautiful shadows of the rings on the spherical planet itself. Just beautiful. Just beautiful. You know, it's just such a beautiful thing, you know. And this is, I mean, this is everybody's favorite planet, isn't it? Right? You know, Saturn's everybody's favorite planet in a sense, right? And so people like to see it. It's really pretty. It really is very pretty. I'm just reading something here that Gas Mask wrote. Yeah, Gas Mask, I get your point. He was saying that, you know, when we look at moons, basically we tend to think of them as round, like our moon, like the Galilean satellites, Io, Europa, Ganymede, and Callisto. Tethys, you know, Miranda, you know, Minos. Miranda's not Saturn, I'm just naming moons. And of course, the moons we do know, Enceladus and so forth, they're spherical. Well, above a certain diameter, a craggy asteroidy type object body will end up self-adjusting itself to be spherical based on the forces of gravity. Every time something strikes the moon, and a piece of it breaks off, it'll tend to help round it out more and more and more, and over time it'll round itself out. There'll be tectonic forces on it, gravitationally, I guess you would call it tidal forces, that will tend to move that moon into a more spherical shape. So you can't have any asteroids the size of the moon, for instance. You can't have an asteroid the size of Mars or even a craggy asteroid the size of the largest dwarf planet in the asteroid belt, Ceres. That's Ceres. Okay, you can't have a craggy asteroid that size, and it's because it's above that limit, that diameter, something around 640 miles, I think. And beyond that, it's going to be a spherical object. It'll tend to that every time. And that's what we observe. I'm glad Earth is your favorite, the gas mask. Brian Levitt, let me answer that question. I don't know if Daryl got to it already. Oh yeah, he did. Okay, yes, they're glass filters that are inside of a actual filter wheel. Okay, it's a 5-position filter wheel, and that 5-position filter wheel has in the first position a very narrow band filter, which takes just slots out of the spectrum that pertain to what the nebulae look like, and shows us, even on a bright moonlit night like tonight, we saw beautiful nebulae with their dark lanes and everything. Filter 2 is a slightly wider narrowband filter. Filter 3 is a spectral filter. And to give you an idea what that looks like, it'll be a taste of what we're going to be doing with the observatory after this gets moved to Arizona. So to give you an idea, all right, this is 5, okay, 4 is black. It's a black disc because we have to get sometimes what we call dark frames. And then this is 3 is a spectral filter, right? And you can see Saturn shows up with a full spectrum. That spectrum is in fact the spectrum of the sun. And when we look at it, we see all of the lines and all of the chemical components that are in the sun. Now, why would that be if we're looking at Saturn? That would be because it's reflected light from the sun. However, this spectrum, red, orange, yellow, green, blue, indigo, and violet, with all the different lines indicating the different elements in the sun, they show up as dark little bands. You know, in this case, they'll be horizontal bands because of the way the spectrum is angled here, but they kind of go this way through that spectrum, which is going this way right now. But we would also see some additional dark bands that aren't in the sun, and those are coming from another place. Those are coming from Saturn's atmosphere itself, absorbing some of that energy. And after it absorbs this energy, what comes back to us in that light is the sun's spectrum minus the elements that were removed by the spectral wavelengths that were removed by Saturn's atmosphere itself. And that's what that's actually what, oh, I don't have it here, it's over behind me. That's what our spectrometer is going to do for us. We're going to have a spectrometer, has a fiber optic cable, it's a slit spectrograph, and it's going to go in to the telescope behind me over there on the table. And when we finally put this one back up, and the telescope in the dome is the Arizona telescope that's going out west. But this particular telescope behind me is going to have a slit spectrograph on it, so we can actually look at very, very detailed spectra, along with doing visual camera work as always, as we've been talking about. But we're also going to look at the spectrum and in detail of objects like this. We'll be able to look at Saturn's spectra and detect in its atmosphere the things that it has in its atmosphere. We'll be able to tell the chemical composition of Saturn's upper atmosphere with this spectrograph. So that's going to be kind of cool. All right. So we'll go back to filter wheel number 2 and then 1. Actually, went the wrong way. Now we'll go to 2 and then 1. There we go. And I'll have to refocus once we get here. Okay. Actually, no, we could go to... let's go to 5 again. Let's do one more shot. Oh, that's nice. Look at that. You can really see the curve of Cassini's division here. It comes right around the front, goes up the side there. And there you can see the shadows of the rings back there. And then that, you can see that crepe ring there really nicely. Look at that.
Uh-huh.
It's semi-transparent across the front. Very, very pretty. Very, very pretty. All right. Okay, let's go now and let's see. Goodbye, Saturn. We like you.
I've said before, I think the strongest reactions I ever got to any object I ever showed people through the telescope was Saturn.
No doubt.
I've been accused of having a picture stuck in the telescope.
Yeah.
I got into a Wayne's World sort of way, no way argument with a young lady one night.
Way? No way.
Way. Whether it was what I was showing her was real or not.
Yeah.
To me, in the eyepiece, the rings are always look white to me, whiter anyway.
Yeah.
And the ball of the planet's kind of a mustard yellow color. Sometimes, depending on how open or closed the rings are, it looks almost like a fried egg.
Yeah. Yeah, that's true. Hey, Terry Groff. Okay, we're looking at this object right now that's coming into view here. This object here is called the Little Gem Nebula. And it's also known as a Green Mars Nebula, or NGC 6818. It's a planetary nebula, the remnant of a star that has literally expelled its outside envelope, basically its guts. Not a supernova, but a gentle sloughing off of material as the star expanded in size as it ran out of hydrogen. And when it ran out of hydrogen gas, which is the main fuel, it would contract. And then that would bring other fuel into the core, and it would heat up tremendously as it contracted and pressure increased, and then it would increase again and blow to giant proportions. And the star would pulsate like this. Many stars will do that pulsation, and as they do, they puff off the outer layers, puff, each time they pulse. When they do that, you sometimes will see concentric shells of material that are puffed off the star, for lack of a better term. And that's what we see here. And let me show you that. Okay, so the nebula we're looking at is right there. So let's try a test shot. 10 seconds at 500. And what are we shooting at, first of all? We're shooting with no filter. We're just looking at it through the lens. So the camera's seeing it without a filter. And we are focused still for Saturn, so it should be focused, but it's going to be a brighter image because the moon is close to us. But we can get rid of that by changing the filter.
And the focus.
That's correct. Okay, so here is doing 10 seconds. It makes it a little easier for us. And it's a fairly bright. There it is. There's the little gem. See that? Pretty cool. Okay, and we probably want to move it more toward the center and adjust focus as well again. We can try it. And you're right, Daryl. We're gonna have to we're gonna have to refocus anyway. So what I'll do, actually, redo that. I'm gonna bring up that star. And we're gonna go get that star. And here we go. Okay. All right. Now we focus on this guy.
Mark, would you excuse me for a moment, please?
Sure thing.
Right back.
I'll be right here. That might be it. Okay. By the way, guys, just wanted to thank you for coming out and hanging tonight. I think that we have been having a good time, because even with moonlight, we're able to get some things that we can see. I've gone 10 seconds here at 500. Now I'm going to go 15 seconds at 500. Again, this is the camera operations. Okay, this is the telescope operations. This operates the north, south, east, west movements of the telescope. This is the telescope computer. This is the focusing of the computer. This down here is the filter wheel. We're investigating. We'll be using that more shortly. And this is the main view, the live view. And this is the telescope, the camera control cluster. And one of the things too that is also important, very important, is along with all these views, we also have the view in the dome of the telescope, which is right there, over there on the side there. You can see it. Okay, this is the telescope view. Okay, you can see the telescope. And now what we'll do is take 15 seconds at 500. And you'll see there comes a point where the moonlight just becomes just too much. Okay, 10 seconds at 500, not so bad. We could see it, but it was sort of faint. If we want to make this object really bright and really look pretty, then we have to take a longer exposure, right? Or change the ISO, that is the settings. And you can see here it's still a little faint and it might be slightly out of focus, so we can go back and work on that. This is what you do, right? When you want to get a good shot, you gotta work at these things. All right, so let me go over and I'll put this right here. Let's start right there, and now it'll be almost dead center for the focus. Here we go. There we go. Okay. Let's run the focus again. You go way out. Okay, going way out and then way in. Okay, maybe that did it. That looks like it might have worked nice. Okay, and let's drop on in. Okay, let's try 20 seconds at 500. Tara, is that supposed to be funny? Hey, Rascally Rabbit, how you doing? That's true. If you remember, Rascally Rabbit says other theories suggest the universe will die cold, dark, and lonely. That's true. Those theories are, that's called heat death. Believe it or not. Why would it be called heat death if it's going to be cold, dark, and lonely? It's because it means that all the objects that have warmth now will have radiated away their heat. So it's called heat death. And that's one of the potential ends. Hey, Supernova. How are you? That's one of the potential ends to the universe is heat death. Yeah. Okay, and Supernova's asking a question. How long do you think the galaxy will be sucked in by the black hole? Well, it may not happen at all. Incidentally, Daryl's computer just apparently rebooted on him. So we'll have to just wait. And at the center of our galaxy is Sagittarius A, as Kathy Prensek just said. And it's something that we won't have to worry about being near, because we're more than 30,000 light years away from it. Actually, we might be a little closer. But we're in an orbit around the galaxy, and we're not coming anywhere near the middle of the galaxy ever. So, but this is the little gem, by the way, and notice how it has this really cool, this really cool little central spine to it. Okay, that's kind of cool the way the little gem looks. It's this little tiny ball. It's a little grapefruit. See, I'm holding a little grapefruit in my hand. I mean, it looks beautiful, and it's again, it's the remnant of a star that puffed off its outer layers as it got into a red giant stage. The blue color is called oxygen 3. It's a transition where oxygen atoms have ionized not once but twice, and those electrons that left the atom came back in, and as they did, they gave off light, and that light is blue, like this you see here. That's the teal color. You can also see a subtle little reddish tinge, which is very common with these kind of planetary nebulae. And the subtle reddish tinge is due to neon and or possibly hydrogen that's causing that red tinge. Now, in order to catch this with a little more detail, what I'm going to do is I'm going to take now and go up to filter number 1. Okay, so now I'm going to go to filter 2 actually, because now I can take filter 2 and focus again, because once you have a filter in place, you have to refocus the telescope. So this has a filter in place. I'm going to bring it up, and I'm going to bring the telescope more toward the object that I want to use to focus. And it's going to be that faint little star that you can barely see in the middle, but I can see it. And now what we're going to do is going to go in there, and there is the star. You can barely see it, but I'll grab it and pull it down. There it is, right there. That's the star. And we're going to focus on that. Okay, Daryl's back. I'm going to call Daryl back, guys. Hang on. Welcome back.
Thank you.
I assume your computer decided to reboot on you?
No, I just pressed the wrong button.
Oh, see, I was waiting. I figured, I told folks your computer probably rebooted on you.
Yeah, I saw that.
Oh,
Can you share screen with me?
Yeah, of course. I thought. All right. Let's bring Daryl back into this. All right. You should be back. You should be able to hear music. Everything should be okay.
I do. Hello again, everybody.
Daryl decided he had to go off and, hang out with some cosmic friends for a little while. That's what it was.
I thought I was unmuting, but I hit the disconnect button instead.
Oh, well. That's okay. Okay, so instead, what I've done now is I took a little gem, and now we're going to bring this back. Actually, I'm going to take a photo just like this to see. I'll do 30 seconds at 1,000. I want to see if we can actually see that the focus is good. Oops. That was smart. Here we go. Supernova asks, what do you think happens when someone goes inside a black hole? Well, it certainly means the end of their lives, long before they get in the black hole. Most likely because the massive X-ray radiation being given off by the black hole, if not the huge magnetic fields, will rip you apart, to be honest. They are extremely potent fields. Not quite focused.
Spaghettification.
That's right. That's right. If you think about it, if you're falling in head first or feet first, your feet at some point are going to feel a far greater gravitational force than your head, and you're going to get stretched. And we know that the human body couldn't react well to that. So if you survived to the point where that happened, you'd be ripped apart by the gravitational forces. And it would be an unforgiving mess. I'm going to tell you. It's unforgiving mess. Let's not do that. Luckily, though, human beings could never end up falling into a black hole per se, because there's none close enough to us that we could actually manage to do that with, which is kind of good news. I mean, that's a cool question, Supernova. I think that's an age-old question as to what might happen if a person could fall into a black hole. I don't relish the thought, actually, of finding out.
I saw it said years ago that that might depend on the size of the black hole. Actually, a smaller black hole would be more likely to spaghettify you than a big black hole. On a really big black hole, you might not even notice when you cross the event horizon. And I saw somebody years ago, they said they were postulating about missing mass and stuff, that we might actually be inside a black hole. That if you took all the expected mass of the universe and made it a black hole, that we might actually be inside its event horizon.
Yeah.
And they juggled the numbers, and it turns out, they say mass becomes infinite in the black hole, but or how did they put it? Though it's said to be, I'm probably misquoting this, but though it's said to be infinite density inside the black hole, that if it's a big enough black hole, that might not really be true, and that actually if they turn the entire universe into a black hole, the density would pretty closely match what we see out in space right now.
That's interesting. I mean, it's very possible, but it'd be beyond super massive black hole, like the black hole in the center of Messier 87 in Virgo, the Virgo galaxy M87, 55 million light years away, and it's 4 to 5 times bigger than our entire solar system. That's the That's the black hole's diameter. That's pretty big. So, is it conceivable that a black hole could be literally the size of the universe and we're inside of it? I don't know.
That horizon.
Yeah, I don't know that that's something possible, because the cosmic microwave background kind of belies that. The cosmic microwave background, otherwise known as the CMB, is that's the farthest thing that we see, and it's the remnant of the early universe. It's the remnant of the very first things we saw, or the very first things that happened in the universe. But it's not right back to the beginning. It goes to, we start seeing some of it hundreds of thousands of years afterwards, because when the universe was first formed, it was opaque. There was no way that anything could get out and get radiated out. As it became more transparent, then light could get out. And so at that point, what we see of the CMB is what we see of that light that has managed to escape at that point. But because of that doesn't match our model for what's inside a black hole. We would say, well, then what's way out there should be what's just inside the event horizon, right? Well, the answer is that it doesn't match our understanding. So I don't think that we're inside a black hole. I think that we are just in a universe that's expanding. And the other thing is, we would not necessarily find that the universe would be expanding. If anything, we'd find it was contracting, because black holes evaporate over time. Now, they do gain mass. When they gain mass, they expand, okay? But that mass comes from the outside, okay? We don't see evidence of that if this was a colossally supermassive black hole that we're inside, we don't see evidence of matter falling into our universe. So that's the only reason why, those are the only reasons why it's probably not something that is happening.
Well, just for the record, I agree with you.
Oh no, but that's fair to ask that. I want to go back to Supernova asking. Supernova, you got some excellent questions tonight. Hey, Fantasy's here. Nice to see you. I saw you've been here for a little while. I didn't get to say hi. Supernova asks, do you think there are aliens like us in the universe? You know what? To be honest, I don't think that's as unlikely as people have said, and I'll tell you why. When you look at the periodic table, and you say, well, how the heck does the periodic table have anything to do with this? The periodic table is full of all these elements that were made in stars previously. Carl Sagan has always said we are made of star stuff. And I like to do my Carl Sagan impression. We are star stuff. Okay? And because of that, one of the things we are more than anything else is carbon-based star stuff. We have a lot of carbon in our bodies. In fact, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are the main constituents within our body, and together they form many different compounds, all based around the carbon atom. And that carbon atom is what makes us very special. Carbon is the granddaddy of all elements in the periodic table. It bonds with more things than any other element in the periodic table. This means that objects that are made of carbon are going to have an advantage. Okay, and we are made of carbon. We have an advantage. Now, if you look at how carbon interacts with other compounds, it makes nuclides. Okay, we have cytosine, guanine, thymine. Okay, amino acids, and these amino acids form something else. The spiral helix, the double spiral helix of DNA, deoxyribonucleic acid. This is the fundamental basis of life on this planet. Every living thing has DNA. And if you look at how our cells operate, DNA is unzipped. Okay, and half of that goes to another place where ribonucleic acid, messenger RNA, is actually used to build up a new other half. And that's a symmetrical duplicate, all right, to zip up another half, and that's how DNA is copied. It uses a template and then copies itself. Now, if you look at that at a macro level, look at the human form. Symmetric down the middle. We are bilaterally symmetric across our center, okay? The way we interact with our environment is through symmetry. 2 eyes, 2 nostrils, 2 hands, symmetrically placed, 2 ears, okay, 2 lungs on the inside, okay. Chambers of the heart are symmetric to each other inside the heart, but the way we interact externally with our environment, 2 legs, 2 feet, 2 knees, we're bilaterally symmetric, and bilateral symmetry could be a consequence of the way DNA replicates, okay. So because DNA and carbon-based atoms making the slurry of life early on here, because that stuff is so very ubiquitous throughout the universe, it appears that carbon-based life is a template that's offered up by the universe. Template. And as a template, this means that if we're talking about looking for other beings that are bipedal, that walk on 2 legs, okay, we might actually have a good chance of seeing that, because it's possible that other beings have evolved in this way as well. They won't look like us. Not at all. And there's nothing that says they should. Okay, because the fact is they don't need to look like us. We look just the way we do because of 5 extinction events that happened on this planet, one of which nearly wiped out all life on this planet. And it wasn't from an asteroid collision. It was from a massive volcanic eruption that occurred in what is now the Siberian region, the Traps it's called. A cap of rock, and I covered a volcanic vent from below. I mean, we're talking massive global scale stuff here. And this magma, or as Dr. Evil says, the magma would seep out and went all underneath this cap of rock until it got to the edge where it was narrow enough. But as it was going through this subterranean rock, it was hitting organic compounds and liberating the carbon from those compounds. So now you have all this gas, this carbon dioxide gas being pushed along with the magma. And when it finally blew out, it was catastrophic. And this catastrophic eruption into the atmosphere sent gigatons, many gigatons, billions of tons of carbon dioxide into the atmosphere in just a few weeks. And what this caused was a global heat up of the oceans, and the heat rising in the water caused less oxygen to be able to remain in the water, because when you heat the water, less oxygen can be held in the water in suspension, and thus a lot of the sea creatures died. And because life had begun in the sea, most creatures on the planet died, all right, during the Permian. And that was over 96% of all life on the planet ceased to exist because of this catastrophic Earth-generated extinction event. So that is something that's interesting, because out of all that, life still persisted. It still persisted. And because of it, okay, because of the Permian extinction event, one thing happened during the Permian extinction that's really cool, and that is mammals, the things that would become mammals, were dominant during the Permian period. Dominant. There were no dinosaurs yet. Okay? Mammals, the things that would have become us, were dominant back then. But the Permian extinction hit them hardest. And then the other creatures, which would have been the reptiles that were just starting to come up, they were not as hard hit by this. And from the Permian extinction forward, thus began the age of the dinosaurs. And then more oxygen was in the atmosphere. We had up to 33% of an oxygen component in our atmosphere, as opposed to 21% today. That's huge. And that meant that the animals could grow bigger, faster, and so this prospect was great, because it meant that now all these animals could happen, could be created. There was a lot of food, a lot of plant life, a lot of meat eaters, a lot of vegetarians, so to speak. And then 65 million years ago, there was the collision with the Earth and an asteroid off the Yucatan Peninsula. The Yucatan Peninsula, the asteroid that struck the Earth was large enough to make an over 110 mile, I think, crater in diameter. And that was bad, because what happened was that spewed so much material up into the upper stratosphere that it spread out in the upper stratosphere and created a cloud, a dense cloud that hid the sun for what could have been years, months to years. And this caused the plants to die. Thus the plant eaters died off, and then the meat eaters that ate them died off. And it's almost sad in a way, because at the time there was a dinosaur called a Troodon, okay? And the Troodon was actually growing in cranial capacity. Its brain case was actually increasing in leaps and bounds. So it makes you wonder, when you hear all these stories about reptilian aliens, is it possible that there was a species somewhere where large reptiles, which seem to be a natural consequence on a planet, might have actually developed intelligence? Maybe. We can't say no, because we don't know. We can't say no. It's possible. So, but the Troodon has been lost to history, as is any progress that Troodon may have made. But, you see, with the death of the dinosaurs, guess who emerged from the shadows? Obviously you know the answer. You're here. the mammals, those little tiny pre-mammals that were still scurrying around, hiding in, waiting in the shadows, were still here. And they emerged from the shadows. And then eventually Lucy, Australopithecus afarensis, emerged in Olduvai Gorge in Africa and began the long journey of the hominins, which ended with Homo sapiens sapiens, which is us. So you can see that the Earth's path to intelligent life was very circuitous. Okay? But, circuitous as it was, it still happened. And it doesn't mean it's necessarily going to happen everywhere, but it did happen here. Just a really, really cool thing, Sleestack, yeah, from the land of the lost. Remember the Sleestack? Yeah, that's something that Rascally Rabbit just talked about. So Supernova, that's a long answer to a question, but I really wanted to be complete. So I know I went on and on and on. So Daryl, if you see any questions out there that you'd like to field, go for it, because I'm okay with you doing that. I'm just showing right here. This is the Gem Nebula, the little gem. See the structure in there? This is with the filter that we took. Okay, when we're looking at it without a filter, looking at it just with just the white light, it looks like this. It's more or less featureless, but when we actually look at it with the filter, okay, you can see how it actually takes on a new perspective. You can actually see this tremendous detail in here. Okay, so there you go. So go ahead, Daryl, if you want, you could go ahead and attack some questions if there's some.
I got nothing.
I got nothing. Okay. Okay.
Still thinking of trying the Helix tonight?
Yep, I am. I just had to wait for the Helix to get to a better spot, and that's right about where it is now. It's just a little bit shy of south. But, see, the sky is rotating in this direction, so the shutter has been aiming in that direction mostly. Do we dare do the moon and blow out people's eyes? Okay.
Question?
Yeah, it was.
I don't know.
Well,
won't be as bad as if you really looked at the moon.
That's true. I'm gonna take us down from all this just to get a look at the moon. Let's see if we can. Okay, we're at 50 ISO, and I'll take us to a 90, a 125th. Yeah, so that'll still be probably a little bright. All right.
When you look at a near full moon through the telescope, folks, it's like staring into a car headlight from about a foot away.
Yeah, he's right about that. He is right about that. It's no fun. And then you don't have any night vision for how long there? About 20 minutes sometimes.
Yeah.
Yeah. Okay, so we're looking at the moon here. Now, it's not that bad tonight because of the fact that I quickly counteracted the brightness of the moon by dropping down some numbers and values here. But if we want to see the moon, let's see how focused it is, shall we? Let's check that out. Let's see what we got here. Actually, it's probably not going to be that bad. Without shadows in some of the craters, you really... The moon doesn't look very, flavorful, But I know that we do have some really interesting stuff up here. Okay. Okay, that crater right there I just zoomed by. I'll come back to and I'll take a photo of that as well. Okay, that's Aristarchus crater up there. Oops, hang on. This is Aristarchus. right? And right next to it is Herodotus. Okay, and looks like we're not bad. I'm gonna take a photo right now and see what we get. Okay, there's Plato right there. Let me take us this way. This is Mare Imbrium, the Imbrium Basin. This is a area of a massive impact at one point in the moon's past. Plato crater is right there. That's 60 miles from here to here. All right. We have Mons Pico out here, which is these mountains out beyond Plato in this area here. These are probably features of material that was a remnant of the ancient collision which might have caused this basin. And those areas were probably pushed up higher and didn't get fully filled in by the lavas which flooded over and filled in this basin, as well as destroyed this crater edge and filled in this crater basin here. So as you can see, the moon is a very interesting place. Okay, now we have over here we have the crater that we talked about. This is Aristarchus crater. Has one of the brightest ejecting patterns, that is ejected material on the moon. And the reason
it is the brightest point on the moon.
Yeah, and the reason, thank you, yes, you're right. And the reason it's as bright is for one reason. Do you know that reason, Daryl, any chance?
How recent the impact was?
Exactly so, good. Yeah, it's because it's actually a young impact relative to some of the others, okay? I think this is like 400 million years old versus 800 million for like Copernicus or something like that. I mean, we're talking, it's half the age of Copernicus. And so the ejecta hasn't had long enough time to interact with, the ultraviolet light that's coming from the sun. So it's still got this, it still has this beautiful, whitish color to it. It's really kind of cool.
Yeah. If you go down to the lower left of our Aristarchus some, it's out of view right now, and it may not be visible yet until after full. You can see the darkest point on the face of the moon, the crater Grimaldi.
Oh, that's way on the edge, though, no?
Yeah, I think so.
Is it darker than Tsiolkovsky?
At least on the visible side of the moon, it's considered the darkest object.
Oh, on the near side, okay. Yeah, that's probably very true. Yeah. Well, at least I didn't blow people's eyes out with it,
Yeah.
Yeah, which is good. And you can see this elaborate ray structure here from the crater Tycho. The moon's gravity is only 1/6 that of Earth, of course. So when something strikes the moon, this ejected material is going to go far and wide. And depending on what the topography looked like when the strike was, that topography is going to shield some of this ejecta from going out. Now, if you look at Copernicus, right up here, you can see that this ejecta went in all directions. It's splattered everywhere. Okay? Tycho, on the other hand, is very different. Tycho only has a ray structure that's somewhat well defined. You don't see it blasted out here and all the way around. The reason for that is that when Tycho struck this area, there were already other craters in this area. And when it dived into the moon and this ejecta went shooting out, a lot of the ejecta got stopped by the other topography in the area, the other mountainous regions. All right, and thus Tycho's ray structure was minimal compared to what you might see with other craters. Again, you compare Copernicus with a splatter pattern here, okay, with Tycho down here, and it's night and day. They look very different. Now, Tycho has a bigger pattern, but you would expect it to actually have more of a splat, and it just doesn't have it because it hit in a mountainous region on the moon already. So that's what's interesting about the moon and Tycho. There's a lot interesting about the moon. But, you know, the moon is the nemesis of the astronomer anyway. At least it was, until we got our narrowband filter.
Mark Isabella asks, have you talked about transient lunar phenomena before?
Oh, Isabella Melamed. No, we haven't talked about transient lunar phenomena. So that's actually a really good thing to talk about. I wish that we could. I wish that we could see some. I know some transient phenomena they've included in that definition are things like the lunar wave, but we know what the lunar wave is from, and unfortunately, it's not from anything like the moon's a hologram or anything like that. It just has to do with superheated air that's heated by passenger jets that have gone by far away from the moon, but air masses drift. And as these warm air masses drift, which are actually fairly confined, they don't dissipate for quite a while. As they cross the moon, that warm air is going to make the moon image look like it's getting warped, like a mirage, as it crosses. And so it looks like someone's refreshing the moon image. You know, they're cool. I've seen them.
You've caught one transient lunar phenomena.
We did, remember?
Yep. And it was in 2019. We talked about it recently.
You're right. And for those of you that are interested to know what that was, it happened during the lunar eclipse. It was, again, proof that the universe is always in action. And what we saw, and Daryl, you were with us, you remember, we had the moon. I'm going to move it up so I can show you. And we were in a lunar eclipse, and it wasn't a completely total lunar eclipse, but we were close. And this part of the moon down here was reddish, very red. Okay, the part up here was a little bit dark red, and there was some whitish area, not whitish, but kind of lighter red. And right at the height of it, right here, just about here, some of the people watching, there were 5,000 or so people watching at the same time on the stream. We saw this white flash right there, a white flash right there, about the size of half the width of the arrowhead up top. Okay, and that I thought at the time was a video glitch because it went this fast. You know, it was like, psh, and it was gone. Well, it turned out that we actually caught a meteor hitting the moon. We were one of 5 groups on planet Earth that actually saw it. And you can go back and see it in our stream. It's back in January of 2019. And we actually caught the flash of the meteor. The meteor was only about 2 feet across. So you'd say 2 feet across, 240 million miles. How could we possibly see that? Well, the answer is that we could see it because of the fact that when we look at the moon, we're watching a moon that's 240 million miles away, but we're also looking at an airless world. 240,000 miles. That's what I meant to say if I didn't. Thanks.
You said 240 million.
I did. That's crazy.
That's a ways away.
Yeah, that's too far away. Yeah, at 240,000 miles away, okay, 250,000 miles, okay, then you'd say, how could we see a 2-foot object hit the moon? I mean, it'd be impossible. We can't see the lunar modules from any Earth-based telescope with the best magnification, nor even the Hubble Space Telescope with the best, modification, best lenses, best capabilities. So how come we could see a 2-foot object strike the moon? What were we actually seeing? What we were seeing, huh?
I'm sorry. Go ahead.
Oh, what we're actually seeing was the energy of motion, which we call kinetic energy, converted into the energy of heat, which was obviously the infrared signature of this object hitting the moon at many miles per second. It was moving.
Bada boom.
Yeah. So when you have an object that's 2 feet across hitting the moon with that kind of speed, maybe it was 25,000 kilometers an hour, 30,000 kilometers an hour, or more. When it hit the moon, all of that energy of motion was converted to heat in an instant. And that becomes a white hot instant mass that you can see for a long distance, including the distance from the Earth to the sun, to the moon, which is 240,000 miles. So you see, it's really kind of an amazing thing. This is a live view of the moon, by the way. We're seeing it live right now. So amazing, I'll tell you.
Some medieval monks are thought to have once witnessed a large meteor hit the moon.
Oh, yeah?
They saw a flash, and they saw a cloud come up over the moon, and it turned the whole moon dark.
Really?
Kind of like that.
Well, that's really cool. This is the narrowband filter now we're looking at right here. And I'm going to just bring us up a little brighter, because I'm going to check something. It'll take a 1/6 of a second. Yeah, see, the focus is not so bad. But you can actually see the, this is Tycho with its ray structure. This filter helps to show us the ray structures a little better. It's kind of cool. So that's neat. Alright, so shall we go to the Helix?
You can try.
I can.
But that's why you got that filter up now.
You think? Now, why would you say that? You're absolutely right. If I hadn't told you before, folks, Daryl's a smart guy. And I think you know that. Okay, now...
you talked about it earlier tonight.
Yeah, we did. Yeah. Now, the Helix is right here. I gotta zoom in so we can actually see it, because this program accounts for the brightness of the moon. So when the moon's in the view, you know, you can zoom in and not see much of anything until you leave the view. See? You leave the view, and you actually end up seeing it brighter. I'm going to get rid of my observatory cam. This might be the one time when we will have to go move the dome. Or will we? Let's see. Oh, maybe not. No, we will. Because I think that this is right on the edge. I should go check before we do this. So, you want to hold down the fort while I go and do that?
Sure.
I'll leave people looking at the moon, so I'll be right back.
Okie dokie. Isabella, I am not prepared to get into a lengthy discussion about transient lunar phenomena. How can it last for hours, though? One type of transient lunar phenomena could be outgassing. Trapped gas under the lunar surface escapes, and it puffs up and might be visible for some amount of time. That's the one idea that comes to mind. There are several kinds of TLPs, and I haven't read up on TLPs in years, but that's one I know. And you've got a pretty specialized kind of a lunar observer who watches for those regularly. It might behoove you to do a Google search or a search engine search on transient lunar phenomena, and they will detail the different types. That's about as far as I'm prepared to go with that right now. And what else is going on? Jeez. Hello, Go Captain America. Folks, it feels like fall here all of a sudden. I mean, summer goes quick in Colorado, but it was in the 90s here a few days ago. The last 2 days, even in the daytime, it's been in like the 60s all of a sudden, maybe to the low 70s, and feeling quite crisp at night. It got back up in the 80s today, but darn it, I still felt cold today. And fall is coming. It's supposed to get down in the 40s tonight. That's the lowest so far this year, or this season. Fall is coming. You're welcome, Isabella. Usually this gets to be the best time of year after Labor Day in the U.S. In Colorado. Best time of year. We just get day after day of week after week sometimes of sunny, mild days and clear, cool to cold nights. But every year is different. Indeed, Katie. Welcome back.
Hey, thanks. What did you regale them with while I was gone?
I tried to answer Isabella a little bit about transient lunar phenomena, how they could last for hours. The one answer that came to mind offhand was outgassing.
Okay.
That might, hang around a while. I haven't read up on lunar transient phenomena in years, so I'd have to go look it up myself.
Well, there's no doubt they do occur and have occurred. The moon is tectonically inactive, as far as we can tell. Did you mention anything about the moon ringing like a bell?
No.
Okay, well, when the moon, when people say the moon rings like a bell, that indicates it's hollow because they think bells are hollow. But that's not what makes bells ring. What makes bells ring is the fact that they're open at one end. Okay? And it creates what's called a standing wave. But a sphere, okay, that's hollow, won't ring like a bell. Okay? It'll go dong, right? Especially if it's made of rock. You can have a bell made of rock, okay? But the thing is, if you want to see the properties that make a rock sound like a bell, one of the things you notice is that you were looking at something that would actually be, I'll just tell it to go there to the Helix while we're waiting. You actually would have to have a rock that's actually solid. And for proof of that, you can go to Ringing Rocks State Park in Pennsylvania. Anyone in the chat, if you're from Pennsylvania, you will look. Isabella, very well done, very well said. Yes, it vibrates, it doesn't ring. Well, ringing includes vibration, but the ringing is the standing wave that's created. I don't know why Katie's comment was hidden. I said I'd let it show. So, but at Ringing Rock State Park, you go there with a hammer and you bang the rocks and they go bing. And it's precisely because they're solid and actually fairly homogeneous throughout. And that solid nature is what makes them act the way they do. So when the moon, you say, rings like a bell, not exactly. But if it does have any kind of residual vibration that can be detected, it's because the moon is solid. It's pretty much homogeneous all through. If it wasn't, then you would look at like a planet like the Earth, right? We send seismic pulses into the Earth, and they go all over the place. Their echoes are all different. And that tells us the structure inside, meaning that the mantle is a plasticky, molten material, and that the outer core is molten and the inner core is solid. Okay, we can detect this through seismic studies. What this tells us, in fact, is that when we look at objects that are solid, we're going to get a very different sound resonant pattern back from those And on the moon, we had seismic experiments that we did, some in place on the moon and some through the willful destruction of boosters that were crashed into the moon. Namely, one of the Saturn rocket stages for each Apollo mission. It was crashed into the moon, and the seismic sensors would detect the crash and feel that vibration wherever they were, because of the fact that the moon's solid nature allowed this vibration to transfer all the way through and move around to the moon, or move all over the moon. So it's a very interesting feature of the moon, actually. I'm climbing up here to I'm gonna try 12,800. No, I'm not. I'm gonna try 20,000. Okay, and we are, if you'll notice, we're on filter number 1. We're on the narrowest narrow band because we are right near the moon. I don't know if we'll have luck finding this, but we're going to go for it. And we're going to go for it for 1 minute. And here we go.
The Helix is a famously dim object, partly because it is so close. I have seen it exactly once, and that was through a Celestron 14-inch telescope, very high-performance telescope. And it had a hydrogen beta filter on it. And even then, you could barely see it.
Yeah. That's visually, right?
Yes.
Yeah. Supernova, sorry I didn't get to your particle accelerator question tonight. I apologize. But do come back again. We can certainly get to it. Thank you for joining us, too, by the way. Gas Mask had already answered it too, I believe, and Kathy was kind enough to throw you something. Traveling faster than light is not something we can do as corporeal beings. We're not allowed to do that. Oh, look at that.
Huh. Well, there you go. Is that with the number 1 filter?
Yeah, it is.
Huh. Can almost actually see a little bit of the helix shape to it.
Well, folks, that's pretty interesting. It's a massive planetary nebula remnant. But you can actually see that, Daryl. That's pretty good considering, huh?
Mm-hmm. I think you need to go back on a dark night.
I think so. And it's actually dead center too. I actually didn't expect this to work. I didn't think it would. So I'm going to, because the focus is the same for the other filter, the slightly wider narrowband. Let's go to number 2 and do another. Let's actually go to 25,600. That's pretty cool.
It is.
What's the diameter of the helix? Do you know?
Not offhand. Let me look.
Okay, if you can find it. I got so many screens up here. I can't afford screen real estate. I'm using 2 different monitors. I've got all kinds of things going on. Hey, Go Captain America. Good to see you. I know you've been here for a while. I just hadn't get a chance to get to you.
Helix Nebula's radius is 2.87 light years.
Okay.
The distance from us is 694.7 light years.
Right, which is very, very close.
Apparent dimensions are 25 arc minutes, which is a little smaller than the other. One of the nearest planetary nebulas.
25 arc minutes. Okay, this is with the other slightly wider narrowband filter. If you notice, we've got all kinds of extraneous light in here. See that? That's a far cry from this, where we actually see the helix. That's not bad. Wow. Wow, indeed. You know what I'm going to do? just for fun, I'm going to go to filter number 1. Filter number 1. Let's go, baby. Okay, 25,600. Oh, do I dare? Okay, 32,000 ISO. We're cranking it. 1 minute. Or am I in a minute and a half? Let me see. Let me go check my settings. The bulb shooting. Okay, it's 1 minute. Oh, Kathy Prenderseck says, I took a few college astronomy courses. One was cosmology. Yeah, the kind of class that answers a lot of questions. If you take physics course in high school, that would actually prepare you for astronomy. That's no doubt. I did. I took physics in high school.
So did I.
That's why you're an astronomer. It's automatic. You learn about the universe, you know.
Our physics teacher was a dirty old man. He taught a fun class though.
Wow.
The girl who came around daily picking up attendance slips for classes, she was a very attractive girl, and he made it a point to take his attendance slip to her during class every day. And one day he fell down on the floor. He was in such a hurry, and he landed on, he hit the floor. So he just lay there and started looking up her dress. What can I say?
Well, as long as you don't say, why didn't I think of that, right? It doesn't...
Yeah.
Wow. Yeah. Well, look, guys, this is the Helix Nebula. We actually could see it. And just so you understand, this big bad moon, okay? Look at this size here, okay? Let me just get these things to be the same size, okay? Let's put that here, and let's put the moon. Where is it? Where's the border? Oh, I can't see the border. Well, the moon is, this thing here is, let's see, the moon's half a degree, just about. So that's 30 arc minutes. This is 25 arc minutes in diameter, you said?
Yeah.
So it's almost the size of the moon.
I don't think we're seeing all of it, but...
No, we're not.
Oh, what we see right there, you might be 15, 20 arc minutes. I mean, I can actually see a little bit of detail. The top left quadrant is brighter than the rest of it, followed by the sort of bottom right quadrant.
Yeah.
And it's dimmest at the top right.
Yeah.
I think a good dark night. Good dark night.
Yep.
You get some good images and stack those, and I think you'll be surprised what you might catch.
Well, I did the Helix one night, remember, but I wasn't using a filter like these, so this would make quite a bit of a difference, I think.
Mm-hmm.
Yeah. Yeah.
Something to look forward to.
Sure is. And just by the way, for everybody watching, I'll be doing a A&E special here, I think either next week or the week after. I'm not sure when. They gotta figure out when they're doing it. And it's going to be on not just astronomical things, but it's going to be more on UFO stuff, which will be kind of cool. So I'll let you know when that's going to air. And hopefully I've got some other really incredible news after that. But on the SkyTour West front, we're going to be moving south into the southwest, right? And this nebula is going to be higher in the sky because we're gonna actually drop 10 degrees of latitude, so we're going to go from like 41 down to 31 or so. And we're going to see this will be 10 degrees higher in the sky, so it's going to be an object that we'll be able to capture in quite a lot of detail. And the dome is not a dome, it's actually a building with a roll-off roof, where I told you 12 foot by 12 foot. And there's going to be 2 initial piers in there, one for our telescope, and then the other one is going to be for another group that's going to be renting that pier. They've already rented it, and they're going to be doing their streams as well. And we'll tell you more about them once they start doing the install their equipment. But then there's going to be a third pier, and so there's going to be the inside of the building's going to be squared off, right? And we're going to have piers at equilateral triangle locations in there. Our pier is going to have the most advantageous location, incidentally, just so you know, because that's how I want it to be. And so the other 2 piers will be in good position too, of course. There's no bad seats. And then we're going to, on that second pier, that'll be their telescope. On the third pier, it'll be a telescope yet to be determined. And we may put in something called an astrograph in there, or a RASA telescope. These are telescopes that are made for doing glorious nighttime imagery, and under a dark sky, they will rapidly win your heart. You'll hug your telescope every night, kind of a thing, if you could. But that all takes money, and this will come from getting some foundation maybe to support us in doing our public outreach. If you like what we do in astronomy, talk to people talk to people that write grants, talk to people that run businesses, talk to people that like to sponsor a SkyTour LiveStream, and we'll, because we have visions of taking this around the country. I've designed a portable observatory that I could take anywhere that will do everything we're doing tonight, but portably. Drive it onto a college campus, drive it onto a elementary school, and open up the observatory, and bam, everybody comes into a viewing van, and they get to watch on the screens. They get to control the telescope themselves. So it'll be like getting to use a high-tech observatory everywhere we go. I think that'd be kind of cool. I don't have to touch it. I'll let everybody else do the work. I think that'd be kind of cool. So that's where we want to go. That's kind of where we want to go. But the Arizona Observatory is step 1. And we're also talking about not just Arizona. Dare I say, we're thinking of SkyTour LiveStream with more than East and West. Maybe there might be another letter in there. SkyTour LiveStream West will be joined by SkyTour LiveStream South, and SkyTour LiveStream North, maybe. All possibilities. I can tell you right now, I have the energy to do every bit of it. Oh yeah.
Rhymes with Crocodile Dundee. Mark, Supernova is being very insistent. Please tell him what day it will be, the UFO show.
I don't know yet, Supernova, because I haven't got a filming date from them, and then they still have to edit it and get it out there. But I've done a lot of these shows. You can see all kinds of stuff I've done if you're interested, on Discovery Channel, Learning Channel, History Channel, Sci-Fi even, and this one's for A&E, but there'll be a lot more. I'll get you the dates as soon as I know. But if you want to look up stuff I've done, you can look for NASA's Unexplained Files. You can look for the series What on Earth. You can look for the Discovery series Contact. In fact, the end of season 1, the season 1 closing episode, I had a little bombshell that I dropped on that one. So season 1 closer of Contact. And then there's other things in the works that, you know, I don't actively seek any of this stuff. It just comes to me because of the background I've had in that whole UFO field. I'm MUFON's chief photo and video analyst, have been since 2008. And, you know, I promote the Mutual UFO Network in spite of the fact that it takes its bumps and bruises from things that happen within. It's like, you know, but the point being, you know, what's an astronomer doing talking about UFOs? Well, I think that life in the universe is probably a foregone conclusion. And if I said that 25 years ago, I'd be laughed out of any academic meeting, any university, any school whatsoever. But nowadays, people who say there's no such thing as life in the universe, they're the ones that would be kicked out. They might lose their tenure for saying those words, because most people in science agree that there is probably life in the universe. I didn't say intelligent life in the universe. Every single NASA mission has been, you know, whether even to the moon or not, has been to locate signs of possible life in the past. Now, not on the moon, because the moon is airless, but there's still theories that hold that maybe something under the moon, you know, in you know, some type of space creature could live. After all, there are potentially living creatures on the moon right now in a state of what's called cryptobiosis. Does anybody know what those are? Do you know, Daryl? Are you familiar with any of this?
No.
Okay, there's some cryptobiotic creatures on the moon right now. They might still be alive.
Was that those giant insects I saw on that, what was it, From the Earth to the Moon? Or Journey to the... I don't know if you know what movie I'm talking about. I think it was a Ray Harryhausen movie, I think, or English, one or the other, or both. I think they were English people who went to the moon, and they fought giant insects under the surface.
Interesting. I don't remember that.
It was like early 60s, late 50s, early 60s.
Okay. Yeah, when it was bad science fiction, but it was all we had, right?
Oh, it was a cool movie.
Well, what I'm talking about, especially the term cryptobiosis, should have got any of you out there. Okay, Supernova, you're actually, you're kind of right. Yes, what's frozen can be unfrozen, but typically carbon-based life forms, you freeze them with the cells. Ice expands, and so it would rupture the cells, and so freezing a human being probably would be fatal to the human being. And gas mask got it. Nicely done. Oh, and Tara got it too. Sorry, Tara, I didn't see that. That's right, tardigrades. There was an accidental crash on the moon of, I think, was it the Israeli craft that was landing on the moon? They had tardigrades on board, and they are there now and will be there forever and ever. Hey, Papa Tom.
That's cheating.
What?
Well,
oh, for life, you mean?
Yeah, I mean, you know, human agency put them there.
Of course, but technically we can't say the moon is lifeless, because we really think that maybe there is a possibility that there's some little cryptobiotic organisms there left by a crashed human endeavor. Yeah. So yes. And it is tardigrades indeed. Yes, and if you look at a tardigrade up close, oh, they'd make such a great science fiction monster. Oh. Those little water bears would make such a great science fiction monster. Their mouths look just menacing, you know? And they got these giant claws on the side, you know? But because they're so small and tiny, we go, oh, they're cute. But make them 12 feet long and with a thirst for human flesh, and now you've got yourself a science fiction movie.
Give them a good gamma ray burst or two, and they probably will.
There you go. Well, Kathy, you know, the tardigrades, you know, they go into that state where they can hibernate for decades and decades. So it's possible that tardigrades can enter that state, which I mentioned is called cryptobiosis, and they could actually be reanimated with the introduction of a hydrating fluid, you know, water and so forth. Is that pretty cool or what? Supernova, I don't know if frozen animation is possible. I mean, there are people that believe it is because they said, well, freeze your head here in this little chamber, and then 150 years from now, when they know how to fix what killed you, they'll thaw your head and stick it on another body. That's quite a risk to take, huh?
Put it in a glass jar like on Futurama.
That's right. That's right.
Mark, will you excuse me for the evening, please? I'm running out of steam here.
Of course, Daryl. And you know what? I'm going to go too. We've had a good time. We had a wonderful time. We're almost 3 hours in. And we'll end with this shot of the moon here because it's just a really pretty image of the moon. But thanks for coming, Daryl. Thank you for being here. And I want to thank all of you guys for coming out. And we will see you next time. It's clear. It's a really beautiful, clear night. But unfortunately, the moon kind of steals some of our thunder. But you know what? It's doing all right. It gave us some nice... It allowed us to have some nice views tonight because we used our special filter. That's right. See, I'm petting it now. Nice moon. Nice moon. Don't fall on me. Don't fall on me. Thanks, Daryl.
Sure thing.
All right, guys. All right, good night, Daryl. We'll see you the next clear night.
Good night. Take care, everybody.
All right, bud. We'll see you later. Daryl Mason, man about town, amazing guy. So yeah, it's possible, yeah, that the tardigrades could still be alive. I just don't know how they'll react to the gamma radiation or the cosmic rays or the sun's ultraviolet radiation hitting them constantly. I don't know the state of them. If the capsule that they're in ruptured all over the moon, then that UV radiation probably would disassemble them over time. So I'm not sure how long they would live, to be honest. I would hate to see, I would actually hate to see them be killed. I would love to know that they survived. Really would. I really would. So let's see. Now, I know I'm always like this, guys. I do this all the time. But let me just go back and see what else there might be. If there's just one more. Because I mark one more object to Antonio. I'm not sure, though. The helix, obviously, we could see, which is amazing for the moon being right next to it. Gosh, that's beautiful. And let's see. Well, we could try that, but that might not work. Okay, let's just keep going. Let's see if we can go up. Or, well, we know we can do that. So what about... Hey, stop. Well, we can try this. Okay, we'll try Mesher 2 before we call it a night. Globular cluster. Also known as NGC 7089. It's 32,600 light years away from the planet. That means the light we were going to see, we'll see from it, left it 32,000 years ago. So think of the state of early humans and where we were in the evolutionary arena. That's at that point, that's when the light that we're seeing today left this globular cluster. So we should be getting to it right now. Okay, here we go. I think we're there. I know you can't see anything, but that's because it's small. However, let's go back to visual for a minute. This is now the straight through view, and there is our globular cluster dead center, 32,000 light years away. And go back to our filter. All right, and now we'll do a 30-second shot at 32,000 and see if we will be in luck. I think we will. Supernova, your question is interesting. If we were to go to another planet a light year away right now, well, there aren't any planets a light year away. We'd have to go 4 light years away to Alpha Centauri, in fact to Proxima Centauri. And let's say we started circling Proxima Centauri B or C, because there's now 2 planets around Proxima Centauri that we know of. And in astronomy, my specialty is exoplanets. So, but yes, if we look back, we would see the Earth in the past if we could go there instantly. We'd see it 4 years ago. Okay, because it's 4 years ago, 4.3 light years. So 4.3 years ago, we would see it. And there you go. There is our final object for the night. It's a tiny little globular cluster that looks just beautiful. Yeah. Oh yeah. This little guy is interesting because, you know, at 32,000 light years away, we're, like I said, we're seeing the light from this guy 32,000 years later. And it's right there in front of us. Really pretty. Yes, sirree. So, with Measure 2, I just want to make that our last object for tonight. I want to thank you guys for coming out. Very much enjoyed your company. I appreciate everything you do for me. And that makes me want to keep coming back and do more stuff for you. So you guys, you have a good evening, okay? And I will see you on the next clear night. Even if it's tomorrow night. Which it may not be based on the weather. But we'll see. Tonight was a very nice night. But telescope's working great. Everything's working great. We're going to keep it that way. Alright, guys. See you later. I salute you. And you have a good night.